there's two parts of a solution. When you add a solute to a solvent, we make a solution. So the two parts of a solution are solute and solvent. If we had salt water, salt would be our solute. It's the particles that are dissolving. If we have the solute and solvent in the same phase, as in they're both liquids or both gases, it's the one we have lesser of. But if we have a solid and a liquid, the solid will be the solute. The solvent is what does the dissolving. So in the case of salt water, salt would be our solute, water would be our solvent, and the solution would be salt water. You can also have lots of solutes in one solvent. As in, if you were making Kool-Aid, you would have the Kool-Aid powder and the sugar would both be solutes, and the water would be our solvent. And then the Kool-Aid that you're drinking is the solution. There's three types of solutions, or three ways we can classify a solution: saturated, unsaturated, and supersaturated. A saturated solution has as much solute as it can dissolved at a certain temperature in a given amount of water. So the max amount that could dissolve has dissolved. Unsaturated is when you could add more solute. So the water has not dissolved as much solute as it could, or the solvent. And then supersaturated is if the water has more solute, or I should say if the solvent has more solute at a given temperature than it should. This is an unstable solution. An example of this would be if you are at a restaurant and you have a glass of tea. If you add just one crystal of sugar to that tea, it's likely going to dissolve. But you don't know that it's dissolved completely and that it couldn't hold any more until you add some more sugar to it. If that also dissolves, then that was an unsaturated solution. If you keep adding so much sugar that eventually it's on the bottom of the glass, that's a saturated solution. Saturated solutions generally are going to have solid at the bottom because as much of it as it could have has already dissolved and all the excess is going to the bottom. Unsaturated and supersaturated solutions do not have solid at the bottom. So a supersaturated solution is if I took that sugar solution that was saturated, heated it up, and then all that extra sugar dissolves and then slowly cooled it. That's how you make rock candy or sweet tea. You can dissolve more than it should at a given amount or at a given temperature. Solids generally become more soluble as temperature increases, while gases become less soluble as temperature increases. We're going to be reading solubility graphs like this one over here on the right. We have a bunch of different substances, each a different color, and it says which of these is most likely a gas. Well, based on this information above, we said gases become less soluble as temperature increases. As temperature increases, we see that Ce2SO4 3 becomes less soluble. So if we had to make a prediction, we'd predict that one would probably be a gas. It might not be a gas. Some solids do become less soluble as temperature increases. But if one of these had to be a gas, we would predict that one to be. Which of these has the largest increase in solubility with an increase in temperature? So in other words, the largest slope. We can see that calcium chloride has a very large increase in a given amount of time. So calcium chloride would have the largest increase in solubility. For this first one, it says how many grams of potassium chloride. So potassium chloride, we find that line. So we're only looking at that one. To saturate 100 grams of water. If we look at our chart, it's how many grams of solute, in this case potassium chloride, for every 100 grams of water. Sometimes people get confused because they see that 100 grams of water and they think they have to do something with that. As long as these match, then we can ignore the 100 grams of water. So we're just reading the chart and saying 50 degrees, follow it up, and then see that that's about 42 grams of potassium chloride. You could have said 41, you could have said 43. It was somewhere in that range. So here, 100 grams of water, so we don't care about the 100 grams of water since that matches. Saturated at 50 degrees is cooled to 20 degrees. How much potassium chloride would precipitate out? Well, we just said at 50 degrees, 42 grams will dissolve. At 20 degrees, that's about 35. And so if we cooled it from 50 to 20 degrees, we would expect 42 minus 35 grams. Or around 7 grams to precipitate out. Because as we cool it, some of that solid will not be able to stay dissolved and should come out as a precipitate. Some problems, though, you're going to have not 100 grams of water. So in this case, we have 300 grams of water. So if you have a problem like this, you're going to set up a proportion. So for every 100 grams of water, how much can dissolve of potassium nitrate at 30 degrees? So find out how much potassium nitrate can dissolve at 30 degrees. So if you said 30 grams, you are correct, but we have 3 times as much water. And if we have 3 times as much water, we should be able to dissolve 3 times as much potassium nitrate. So you can solve that a couple of ways. You can divide those and then multiply by 300. You can multiply those and then divide by 100. Or you can see that it was a 3 times increase in water, so we should have a 3 times increase in salt. It's not clear, but here we still have that 300 grams of water, but now we've heated it to 70 degrees. So how many more grams of potassium nitrate would it take to make it saturated? So at 30 degrees, we have 90 grams in 300 grams of water. At 70 degrees, we have about 130 for every 100 grams of water. But again, we have 300 grams of water. So we have 390 at 70 degrees Celsius. So 390 minus the 90 we already had, we would need to add 300 grams to make it saturated. So I just found the difference between what I already had in the solution and what would make it saturated at 70 degrees. The next type of problem that you could see is when it says, what type of solution do you have? We're looking for, is it a saturated, unsaturated, or supersaturated solution? So we find the line we're talking about. We're talking about KNO3. And then it says we have 100 grams of water, so we can ignore that. 80 grams at 50 degrees Celsius. So we're going to find 50 degrees Celsius, and we're going to find 80 grams, and we're going to put a dot there. Notice that that dot is above the line we're talking about, which means we've dissolved more than we should have. We should have only been able to dissolve 60 grams, but we've dissolved 80 grams. So this is a supersaturated solution. So you may want to make note when the dot is on the line, it's going to be saturated. If it's below the line, it's going to be unsaturated. And if it's above the line, it's supersaturated. And again, we're talking about the dot. They're going to give you an amount and a temperature. You put a dot at that temperature and amount and relate it to the line. That's if it's at 100 grams. If it wasn't 100 grams, we'd have to think a little bit more on that. So for the next problem, we have 500 grams of water at 80 degrees, and then we cool it to 20, and it just wants to know how much would still be dissolved and how many grams would have precipitated out. So we have two questions here. I'm going to pause the video and figure out those two questions. Restart when you're done. So we're looking at the NaCl line. For the first line, it wants to know how many grams will still be dissolved. Well, at 20 degrees, we can dissolve about 38. So around 38 grams will be dissolved at 20 degrees. To find out how much will precipitate, we need to say, well, at 80 degrees, it could hold 40. So 40 grams minus what it can still hold is 2 grams, or around 2 grams. Go ahead and pause the video and try this one on your own. Remember that we're looking for saturated, unsaturated, supersaturated. So your KNO3, it was 100 grams of water, 60 grams, and 50 degrees Celsius. So 50 degrees and 60 grams, that's on the line. So this would be saturated. If we had been given 70 grams, though, that would have been supersaturated, and if they had said 50 grams, that would have been unsaturated. Go ahead and pause the video and try this next one. Notice that we're at 300 grams of water, so you should be setting up a proportion. So at 30 degrees, we can dissolve about 10 grams in 100 grams of water. So 10 grams in 100 grams of water. Since I have 3 times as much water, I should be able to dissolve around 30 grams. Go ahead and pause the video and try the next one. Again, we don't have 100 grams of water, so you should be setting up a proportion. So here at 80 degrees, we can also dissolve about 10 grams. So 10 grams in 100 grams of water, but we have 50 grams of water. Since we have half the amount, we should be able to dissolve half the amount. This one's not in your note packet, but go ahead and pause the video and figure out which gas is most soluble at 20 degrees Celsius. If you said CH4, you're correct. At 20 degrees, it has the highest solubility. Helium would have the lowest solubility. And then this graph is in your note packet, but go ahead and pause the video and figure out how much KClO3 will dissolve at 30 degrees in 100 grams of water. So if you said 10 grams, you're correct. So we have 30 degrees Celsius, we followed up, and that is about 10 grams. And it was 100 grams of water, 100 grams of water, so we didn't have to multiply or divide. So we haven't talked about pressure though. Pressure has no effect on solids or liquids because their particles are already so close together that increasing the pressure won't cause more to dissolve. But if you increase the pressure on gases, you're going to increase their solubility. So here we have gas. The gas is the red particles. As you increase the pressure, then more of that gas goes in solution. So in summary, you may want to write this down even though it is in your notes. To make more solid to dissolve, you can only increase the temperature. To make more gas dissolve, we want a lower temp and higher pressure. Think soda. Soda is bottled under high pressure and we keep it at colder temperatures, such as the fridge. When you put that soda in the heat, it causes it to explode because that gas is not staying in the solution any longer. Another thing that we need to look at whenever we're trying to figure out will something dissolve is its polarity. Polar and ionic solutes will dissolve in polar solvents. So if it's polar or ionic, it's going to dissolve in polar solvents generally. And nonpolar solutes dissolve in nonpolar solvents. Often you'll hear the term like dissolves like. The reason being is polar and ionic both have slightly positive, slightly negative, or straight up positive, negative charges, and they're able to attract each other better, causing them to dissolve in each other. While nonpolar doesn't dissolve very well in polar solutes because it can't form as strong of attractions. Here we see an example of ionic solids dissolving. When we have an ionic solid dissolving in water, we've talked about it previously, but the positive ion will get surrounded by the water or polar molecule where all the slightly negatives are facing the positive ion. And the negative ion will be surrounded by the slightly positives of water or whatever that polar molecule that's dissolving it is. Along those same lines, we also have the vocab words miscible and immiscible. Miscible, I like to think of as mixable, because miscible would be when both the solute and solvent are liquid and both liquids are soluble in each other. Here we have some antifreeze or ethylene glycol and water. They're mixing together. Food coloring and water, those are miscible. While immiscible, like oil and water, they're going to form different layers. So the two liquids are not soluble in each other. Here we have some solutes and some solvents. To solve these types of problems, when you see them on practices or on your quiz or test, you need to think water. Water is polar. CCl4 is nonpolar because you have the same thing all the way around. NaCl starts with a metal, so that would be ionic. Since it's ionic, it should dissolve in the polar solvent. I2 is nonpolar because it shares its electrons equally, therefore it would dissolve better in the nonpolar solvent. One more together. This is not ionic, even though it ends in OH. This is polar because it's a hydrocarbon with OH. It's not sharing its electrons equally, so this is polar. Polar would dissolve better in water. Go ahead and pause the video and do those last 5 on your own. Restart to check yourself. KNO3 was ionic, so it should have dissolved better in water. Calcium hydroxide is a base, but it's ionic as well, so it dissolves better in water. Bromine is nonpolar, so it dissolves better in CCl4. If it's just CNH, it's nonpolar, so that dissolves better in CCl4. And iron 3 chloride is ionic, so that dissolves better in water. To make something dissolve faster, you probably already know these. Think to yourself, what are some ways that you can make that sugar dissolve faster in that tea? So one way is to stir it. So stirring the sugar makes it dissolve faster. You probably aren't heating it up, but if you heated it up, it would dissolve faster as well. And finally, crushing it up. Crushing it up means more surface area. If you have a large piece versus 4 smaller pieces, the large piece can only get dissolved on the outside, while the 4 smaller pieces, now we've got 16 times as much surface from these pictures, and so crushing it up means more surface area. Smaller pieces is more surface area, it dissolves faster. Make sure you know what that means, because sometimes when we say more surface area, people think that that means bigger pieces, but that means smaller pieces. Go ahead and pause the video and read this one to yourself. Restart when you have an answer. So if you look at this one, it's saying that we stirred it and we still have crystals remaining. And so we want to dissolve the remaining sugar crystals. So increase solubility. Not necessarily faster. We just need to make more dissolve. So to make more dissolve, we could add thermal energy being heat. If I heat it up, that sugar would dissolve. Go ahead and pause the video and restart this one when you're done. So this one says dissolve faster. To dissolve faster, I want to increase temp, I want to stir, or crush it up. Decreasing temp would make it slower. Stopping stirring would make it slower. Pressure has nothing to do with it. And crushing it up would make it dissolve faster. So D was our correct answer. Last thing you need to know about solutions is electrolytes. You may have heard the term electrolytes in commercials for Gatorade or Powerade or any sports drinks. Electrolytes are simply solutions that conduct an electric current. So they have ions in them. So for Gatorade or for Powerade, they may have sodium ions and potassium ions because you need those ions for your muscles to work properly in the sodium-potassium pump. We have electrolytes are simply acids, bases, and salts. We saw previously that strong acids and strong bases are strong electrolytes, but weak acids and weak bases are also electrolytes. They're just not as strong of electrolytes. They're weak electrolytes. But all acids, bases, and salts being simply ionic compounds, aka start with a metal, or NH4, are going to be electrolytes. Non-electrolytes are going to be covalent compounds, again with the exception of acids, since acids are electrolytes. So for this first one, it starts with a metal, so this is a salt. And if it's a salt, it's an electrolyte. For our next one, remember that that's not a base, even though it ends in OH, it's going to be a metal hydroxide. So this is a non-electrolyte. It's a covalent molecule. One more together. This next one starts with H, so it's an acid, so it's an electrolyte. Go ahead and pause the video and do the other 5 on your own. Restart when you're done. This one started with an H, so it was an acid. Started with an H, so it's an acid. It's not an acid, it's not a base. It doesn't start with a metal, so this is a covalent molecule. So a non-electrolyte, that's glucose. This one starts with a metal, and it ends in OH, so that's a base. So that's an electrolyte. And starts with a metal, so electrolyte.